Hi there, Mr. Sutton here, bringing you the AB Calculus 511 Part 2 homework solutions on using fundamental theorem of calculus to find function values. On this calculator-based problem, they're telling us that f prime of a function is the square root of 1 plus 2x cubed, and f of 2 of said function is 0.4. Based off this, they want f of 5. So we can use our fundamental theorem to figure this out. We just need to do f of 2, or 0.4, plus the integral from 2 to 5 of this f prime function. So basically we're taking our starting value and adding the total change from 2 to 5 to get the new value. So let's do this on Desmos. So to do this, first let me enter in my f prime function. I can't call it f prime though, I'm going to have to call it something else like g. It doesn't like primes for the original function. So we've got sqrt, square root of 1 plus 2x cubed, and now I can use that. I'm going to use it like I did here. Instead of saying f of 2, I'm just going to write 0.4 plus integral, int, from 2 to 5 of, and now I can just do g of x dx, and that's going to come out to about 29.005. which matches up with answer choice A. On this calculator-based problem, they're telling us that h of x is an antiderivative of this weird hybrid rational function with a trig function in there. If h of 5 is pi, they want us to tell them h of 2. So we're going to use our fundamental theorem. Basic idea is we need to do h of 5 plus the integral from 5 to 2 of h prime. Now what is h prime going to look like? Well, if h is an antiderivative of all this, that means that h prime is actually going to be this original thing here. Because h is the antiderivative, so this is the derivative here. So I'm just going to write down h prime is that thing right there, x cubed plus sine of x over x squared plus 2. So we're going to do then h of 2 is going to equal h of 5 plus the integral from, again, we got to go 5 to 2, starting value to ending x value, 5 to 2 of h prime of x dx. And I'm going to do all of this on the calculator. So let me go to Desmos and clear out whatever's already in there. And I'm going to define my h prime. I'm just going to call it g. So g equals fraction x cubed plus sine of x over x squared plus 2. And now h of 5, again, they said that that was pi. So I'm just going to write pi for pi. So pi plus integral, int, from 5 to 2. Make sure you don't have it backwards. And I'll use a g of x because that's what I defined h prime as. So g of x dx. And that's going to come out to negative 5.867. And that's going to match choice B. For this problem, the derivative of the function f is continuous on the closed interval 0 to 4, and values of the function and its derivative are given in this table. We are told that the integral from 0 to 4 of f prime is 8. Based off of that, we want to find f of 4. Okay, so in situations like this, it's helpful if we have a starting value. So we can say that since we're given the integral from 0 to 4, in order to get f of 4, we need to know what f of 0 is, because then we could do f of 0 plus this integral, and that would get us to 4. So my setup then, in general, I'm going to say f of 4 equals f of 0 plus integral from 0 to 4 of f prime. F of 0 we can look up in the table. That's just 5. And they actually told us this integral already. They said it was 8. So 5 plus 8 is 13. That's all we had to do on this one. So that's choice E. On this problem, we've got a picture of Snoopy, apparently. This is actually a graph of g prime. And we're asking if g of 0 is 1, what's g of 3? So this is one of these problems where you have one function value, and you need to use a starting function value plus the integral of a derivative to get some other function value. Okay. So g of 0, we can say, or g of 3 rather, we can say that's going to be g of 0
plus the integral from 0 to 3 of g prime. And let's go a little bit further. So g of 0 they told us was 1. Doing this integral now, we're going from 0 to 3. So we have two areas to add. We have this semicircle, actually quarter circle. So that's going to be 1/4 times pi times the radius 2 squared. Plus, we also have this half triangle here, or I guess it's its own triangle. So 1/2 base of 1 times a height of 2. And let's keep going now. So we have to simplify this because they have simplified answer choices. So this is 1 plus, well, this is just going to be pi, 1/4 times 4 times pi. And this is just going to be 1. 1 plus pi plus 1 is 2 plus pi, or pi plus 2, either way. So that gives us answer choice B. For number 8, we've got a function defined on the closed interval from -3 to 4, and we're told that f of 0 equals 3. The graph up here is the graph of f prime, the derivative of this mystery function, and they're telling us we've got a line segment and a semicircle, so it's exactly what it looks like. Okay, we want to find f of -3 and f of 4, showing the work that leads to those answers. Let's start with f of -3. So for both of these, we're going to need to use our fundamental theorem. So we have a known value here, f of 0. So we basically have to add f of 0 to the integral from 0 to whatever x value they're giving us down here. So we need f of -3 equaling f of 0 plus the integral from 0 to -3 of f prime. And we've got f of 0, we said that was 3. And then this integral from 0 to -3, we're integrating backwards, and we've got two areas to take into account. So this first one is a negative area, but because we're integrating backwards, we're subtracting it anyway, so it ends up being a positive area. This is going to be 1/2 times a base of 2 times a height of 2. And then we have this other area here. Normally this would be positive, but since we're going backwards, it's a negative 1/2 times 1 times 1. And this is actually good enough for the free response. We should leave this unsimplified. But if you really wanted to know what it is simplified, we've got 3 plus 2 minus 1/2. So that's 4.5. All right, let's take a look at f of 4 now. That's going to be f of 0 plus the integral from 0 to 4 of f prime of x dx. Again, f of 0 was 3, so it's just this other integral over here. Now for this one, this is going to be negative area, but it's kind of interesting because in order to find this area, we have to take a rectangle and subtract this semicircle from it. So the rectangle has a base of 4 and a height of 2, so 4 times 2. And from that, we are subtracting this semicircle, whose area is going to be 1/2 times pi times the radius 2 squared. But then we're subtracting all of that. So here's what it looks like. So we have 3 from f of 0 minus, and now here's that area below the x-axis. Here's our rectangle, 2 times 4. Here's our semicircle. So what does this all come out to? Again, you don't need to simplify this, but if we really wanted to, we've got 3 minus 8, so that's going to be a -5. And then we've got minus minus, so plus 2 pi. So then altogether, 2 pi minus 5. For number 9, this is part D of an open response problem where we have the graph of f prime, which is twice differentiable. They've told us some stuff about horizontal tangents that we're not actually going to need in this part of the problem. They did tell us the areas of the regions here and here are 9 and 12 respectively. So we've got 9 over here, 12 over here. Good to know. Given that f of 1 equals 3, they want us to write an expression for f of x that involves an integral. And then they want us to find f of 4 and f of -2. So I usually answer questions in the order that they're asked, but this time around I'm going to actually find f of 4 and f of -2, and then I'm going to go back and write this expression for f of x that finds any f of x value using an integral. So f of 4. Using our fundamental theorem of calculus, we can write that f of 4 equals a value that we know, f of 1, plus the integral from 1 to 4 of f prime of t dt. So this expression here, we know again that f of 1 equals 3, and now we're going to add the change in f from 1 to 4. That's what this integral represents. So to do that, we need the area under the curve between 1 and 4. Now this is negative area. They told us that area was 12. So this is going to end up being 3 plus negative 12, which comes out to negative 9. Didn't actually need to simplify that to negative 9, but we just did. Now we're going to find f of negative 2. That's going to equal f of 1, which again we know, plus the integral from 1 to negative 2. Now this is kind of like the last setup here, but we're going backwards. We're integrating backwards this way. This area down here they said was 9, but because it's under the x-axis, it's going to be negative 9. But because we're integrating backwards, we're going to be subtracting negative 9. So we're doing 3 minus negative 9, which again does not need to be simplified, but comes out to 12. Okay, now we have to go back and answer the first part of the question here, where they wanted the expression for f of x. This is any x value that you want to plug in. So whatever these numbers you were that we're plugging in, those were going to be the upper limits of integration in this expression here. So we're still going to have f of 1, which I'm now going to just write as 3, plus the integral from 1 to something of f prime of t dt. But now what should I put up here for a variable? Well, I can't put t because I'm already using that inside the integral. I need one of those dummy variables up here. And since they want an expression for f of x, we're going to make that variable x. So altogether then, we've got f of x equals 3 plus the integral from 1 to x of f prime of t dt. On this no calculator free response problem, we have the derivative of f given as f prime, which they gave us as both a graph and also as this nice little piecewise function. And let's see, the graph of the continuous function f prime shown above, they're saying has x-intercepts at x equals negative 2, which is about what it looks like. And this is actually pretty helpful, 3 ln of 5/3, this spot right here. Because otherwise, I mean, how would we know without a calculator? So they also told us that this part right here is a semicircle, which will be useful, and f of 0 is 5. So based on all this, our first task is to find all values between negative 4 and 4 where this graph of f, which they did not show us, has a point of inflection. So if I want to know where f has a point of inflection, one way to figure it out based off of f prime is to see where f prime is reversing direction, which is to say changing from increasing to decreasing or decreasing to increasing. Taking a look at this graph here, f prime reverses directions at 2 spots, at negative 2 and also at the origin at x equals 0. So I'm going to write here just to justify this, f prime changes increasing to decreasing or decreasing to increasing at x equals negative 2 and 0. Therefore, f has a point of inflection at x equals negative 2 and 0. For this part of the problem, they want us to find f of negative 4 and then f of 4. So to find f of negative 4, since I have f prime here and I also have a function value for f, I basically need to do f of 0 plus the integral of f prime from 0 to negative 4. So the way I'm going to write this is f of negative 4 is going to equal 5, which we know to be f of 0, plus integral from 0 to negative 4 of f prime of x dx. And now let me actually write out what we're doing with this integral. So basically, we're finding the area under the curve here. The only thing we have to be a little bit careful about is since we are integrating backwards, because our lower limit is actually a higher number than the upper limit, whatever area we get from negative 4 to 0, we're going to have to negate that area. So to find this area, let me just rewrite the 5 here. We need basically a rectangle minus a semicircle to get this area between the semicircle and the x-axis. So the rectangle, and I'm going to subtract all of this, by the way. Normally this would all be positive area, but I'm going to subtract because we're integrating backwards. So I'm going to do 5 minus, and now here's the rectangle area. We have a base of 4 times a height of 2. So and I'm going to put all this in a big bracket here that I'm subtracting from 5. So we have our rectangle minus our semicircle, which is going to be 1/2 pi r squared, which in this case is 1/2 pi times 2 squared. So all of this, again, would give us normally positive area, but we are subtracting it because we're going backwards. Now let's just see what this comes out to. I'm negating everything in here. So this would normally be, let's see here, half of 4 pi is 2 pi. It would be negative normally, but I'm negating the whole thing, so this is a positive 2 pi. And then I have 5 minus 8, which is going to give us negative 3. So 2 pi minus 3 is the value of f of negative 4. Now let's take a look at the value of f of positive 4. Same kind of idea. We're going to start at f of 0, or 5, and then we're going to add the integral now from 0 to positive 4 of f prime of x dx. But now what is this going to look like? We can't really do this geometrically, but we do have a piecewise function that tells us exactly what the formula for f prime is from 0 to 4. So we're now going to take the antiderivative of this exponential expression here. So going from left to right here, so here's my 5 plus, and now here's my antiderivative in an evaluation box. Let's see, 5e to the negative x over 3. The antiderivative of that would be basically 5e to the negative x over 3 divided by the derivative of this interlinear function. The derivative of the stuff inside here is negative 1/3. So multiplying by the reciprocal of that, you're basically multiplying by negative 3. So this ends up being negative 15 e to the negative 3, or negative x over 3. There we go, that stuff. Minus, this is going to be 3x, just using my reverse line rule. And all of this is being evaluated from 0 to 4. So we've got 5 plus all of this stuff with 4 plugged in, minus all of this stuff with 0 plugged in. And you have to be careful here. Often the stuff that has 0 plugged in just kind of goes away. That doesn't turn out to be the case this time around, so you always have to double check and look. So let me go through and simplify this now. I actually don't have to simplify this. Believe it or not, because I have all real constants here, I could leave the problem in this form and move on, and this is algebraically, numerically equivalent to the correct answer. But if you want to risk it and simplify it, we have this 5 in the beginning. We have this negative 15e to the negative 4/3. This is going to be minus 12. And over here, well, this is basically 15 times e to the 0. E to the 0 is just 1, so we have a negative 15 in here. But we're negating that, so that becomes a positive 15. And then this 3 times 0 is actually gone. This is the only thing that goes away on its own. If you want to simplify further, we have, let's see here, there's going to be a total of 3 over here, plus the 5 is 8. So 8 minus 15e to the negative 4/3 would be the final simplified answer of this. For this last problem part, they want us to find where the absolute max occurs for this function for f. Now, normally we would use the candidates test here, and we would test out the endpoints, negative 4 and positive 4, which we actually have found f of those values, so we could use those at least. We'd also have to test out critical values. So that would include right here at negative 2, and also this other critical value for f prime. This would be, this is 3 ln of 5/3. But those are going to be kind of a pain to plug in. So one way to completely avoid all that work, since we actually only have one local max here, where f prime is changing from positive to negative, we can skip all that by just showing a little bit of sign analysis. So the way I'm going to write this, the way I'm going to justify this, is that f prime is greater than or equal to 0 on the interval from negative 4 to 3 ln of 5/3. So from here to here, our derivative of f is positive, or at least non-negative. This tells us that from this point to this point, f is increasing that whole time, or at least it's not decreasing. It's not getting any smaller. So you've done nothing but increase basically when you get to this point. After this point, f prime is negative between 3 ln of 5/3 and positive 4. So after this point, f is only decreasing. Well, if you've been doing nothing but increasing until here, and then you're decreasing after that, this right here, this has got to be your highest spot. Because if you were increasing this whole time, nothing back here is going to be higher than this spot right here. And if you're decreasing after that, it's not going to get any better than right here. So this proves that f has an absolute max then at x equals 3 ln of 5/3. For the next set of problems, we have a graph of g prime, and they're telling us that g of 2 is 5. And this is all for -3 to 7, that interval. For the part A, they want us to find x-coordinates of points of inflections for the graph, and then justify the answer. Okay, and they're asking for points of inflection for G. Now this is important because they gave us G prime. So if we already have G prime, to find points of inflection, we just need to figure out where G prime changes directions, either from increasing to decreasing or decreasing to increasing. So as we watch the graph of G prime here, we see that we're changing from increasing to decreasing here at x equals 1, and from decreasing to increasing at x equals 4. Therefore, we can actually go straight to the conclusion, G has points of inflection at x equals 1 and x equals 4. For this problem, I'm trying to find the absolute max of G on the interval from -3 to 7, and I have to justify it. So for this, I'm going to use the candidates test. So I'm going to basically plug -3 and 7, the endpoints, into the G function, and I'm also going to plug in any critical values that I need to test in between. So for critical values, that's going to be places where G prime equals 0. Looking at the graph here, G prime equals 0 at -1, 2, and 6. So that's 3 places we might actually have to test out. However, if you look at the sign of G prime, we're changing from negative to positive at x equals 1 and also at x equals 6. So those two spots are actually local mins. There's no way that the lowest value in a region is going to be the highest value for the whole graph. That doesn't make any sense. So in order to not have to test out -1 and 6, I'm going to be a little bit clever and write G prime changes from positive to negative only at x equals 2. This efficiently tells the graders, hey, I'm just going to test out x equals 2 because these other ones are not local maxes. Only x equals 2 is a local max. So if you do this, then you only have to test out x equals 2 along with the endpoints. But now we have to test them out. So to do G of, let's see, -3, I'm going to have to do G of 2, which is 5, plus the integral from 2 to -3 of G prime of x dx. So now to go from 2 to -3, so I've got that 5 again, that's my initial value. To go from 2 to -3, I'm integrating backwards, so stuff that used to be negative is going to be positive and vice versa. So the first area I need to do going backwards is this triangle up here. So this would be 1/2 times a base of 3 times a height of 1. But since I'm going backwards above the x-axis, that's actually negative area. So -1/2, 3 times 1. And the other piece I need is this triangle that's under the x-axis. That would normally be negative, but since I'm going backwards, it's going to be a positive area. So I'm going to have a positive 1/2 times a base of 2 times a height of 4. And I actually do need to figure out what this simplifies to so I can compare it to the other values. So let's see now. I've got 5 minus essentially 1.5. And then over here, this is 4. So that's going to be 7.5 overall. So careful with the math. This was not a calculator question. Next, I need my critical value, G of 2. Now the good news is we know what G of 2 is. They told it to us. So we kind of get that one for free. But we're going to write it down just to show that we're considering the critical value along with the other values. Finally, we need to do G of 7 here. So that's going to be my G of 2, 5, plus the integral from 2 to 7 of G prime. So here's x equals 2. To get to 7, we need to add these triangle areas in there. This first area is going to be negative since we're going to the right and we're under the x-axis. So that's going to be minus 1/2 times a base of 4 times a height of 2. And then we've got this other little triangle here that's positive. So that's going to be plus 1/2 times a base of 1 times a height of 1. Adding all that together, this is 5 minus 4, which is 1, plus 0.5 is 1.5. And we wanted the absolute max value. So that means that 7.5 is our absolute max for this one by the candidates test. For this next one, we're trying to find the average rate of change of g of x on the interval from -3 to 7. So for this one, we're essentially doing g of 7 minus g of -3 over 7 minus -3, or 7 plus 3. The good news is that we already know what g of 7 and g of -3 are. You actually found them in an earlier problem part here, in part B, you found that g of 7 was 1.5, g of negative 3 was 7.5. So we've got then 1.5 minus 7.5 over 7 plus 3. And you could actually leave it like this. This is a perfectly acceptable answer. No need to simplify. But if you are going to be risky and simplify, this is negative 6 over 10, which reduces to negative 3/5. For this last problem part, they're asking for another average rate of change, this one for g prime on the interval from negative 3 to 7. And they have another follow-up part of the question, but we're going to do the average rate of change of g prime first. So that's going to be g prime of 7 minus g prime of negative 3 over 7 minus negative 3. Now the good news is we can just look these values up in the graph, and they even gave us the full points on each of these. So g prime of 7, that's just going to be the y value there of 1. For negative 3, we've got a y value of negative 4. So we've essentially got 1 plus 4 over 7 plus 3, which, if we wanted to, we could reduce to 1/2. We actually don't even need to do any part of this problem, but why not? All right. So the next part is, does mean value theorem applied on this interval from negative 3 to 7 guarantee a value of c for negative 3 less than c less than 7 such that g double prime is equal to this average rate of change? Why or why not? So they're asking, does the mean value theorem apply here? Does the mean value theorem guarantee that we're going to the derivative of this function somewhere equals 1/2? So let's review mean value theorem. For mean value theorem to apply, we need continuity across the whole interval. And we do have continuity for g prime. There are no breaks anywhere in here, so that piece is fine. We also need differentiability across the open interval from negative 3 to positive 7. Do we have differentiability everywhere? Well, not really. We've got corners really all over the place. Specifically at negative 1, positive 1, and positive 4. Because we have these non-differentiable corners on the open interval from negative 3 to 7, the MVT does not actually apply here. So the answer there then is no, because of those non-differentiable spots.